All right, so now I'm going to talk about specifics regarding VFDs, and I'm going to focus for the most part on the Teco line because I was able to, when I started researching, I started leaning more and more towards that brand, so I started doing more research on that brand. And one of the drives that comes up a lot is the Teco, I think it's either the FM or TM50. I think that's the drive that keeps popping up. Factory Mation sells those drives cheap. I mean, I'll probably put an example up here on the screen just to give you an idea of what you can buy one of those drives for. And that was like, when I initially was looking, I was like, boy, that's probably what I'm going to end up getting. I'll probably go with Factory Mation and get this drive. And then I realized when I started researching it a little bit more, I was wondering about this other drive that I had come across, and from the same manufacturer. And then I started doing a little bit more research, and that's when I started learning about sensorless vector drives, because I kept seeing this term pop up, sensorless vector. Okay, and I was like, sensorless vector? What the heck? So I was like, okay, I need to find out what this is, because I got to find out, do I want it? Because it's going to cost me more money to buy a drive that has it. And is it going to be really that great of a thing? So then I needed to learn more about how variable frequency drive works, and then I started learning about flux vector and open loop, closed loop, yada, yada, yada. Again, getting way too technical. Let me just break it down for you this way. The high-end variable frequency drives can do things that these drives that we're using can't do. But we don't really, when I say we, I'm talking about the small home shop owner who's running a mill, an old manual mill or a lathe or something like that. We're not going to be as concerned about this. See, a lot of these VFDs are used in industry to run process industrial equipment and other things where they have very specific needs. And a lot of those really high-end VFDs are going to actually be packaged with a motor, a specific motor. So it's going to be like a custom put together package, and the reason why is because the motor is going to have something in it called an encoder. And what an encoder does is the encoder basically sends information, feedback, back to that microprocessor in the VFD to tell it exactly what's going on with that motor. To tell it, it has a lot to do with varying load conditions, the position of rotation on the motor, and the way it was explained to me was this. I believe that those would be classified as the flux vector or closed loop when they have the encoder. So the way it was explained to me, so that I understood it, was this. Those drives are capable to do some crazy things, like provide full torque at 0 RPM. What? I know, right? When I first heard it, I was like, yeah, no. We know what torque is, right? So how can you have torque at 0 RPM? How can you have a motor shaft that's not turning but has torque? And this is how it was explained to me. Say you had an application like an electric hoist, and you had the cable wrapped around the drum, and that weight, the load, is pulling that cable down as it's unraveling, okay, as it's lowering, okay, and then you stop the motor. So as that load's coming down, what's going to happen is when it stops, well, the motor's going to, die down, okay, and come to a stop slowly. You can have some kind of braking on there and everything, but if you want really precise control and you want to be able to make that motor stop in a very precise short time and then hold in that position so that the weight is pulling on that thing and trying to rotate that shaft, but no, the VFD is still sending enough power to that thing so that that shaft isn't rotating. And it's not rotating the other way, it's starting to lift the load back up, but, alright, so, getting off the subject here, let's just sum it up this way. we don't need a closed loop system. We don't need a motor with an encoder for, and again, when I say we, I mean us guys who are just trying to run our old manual lathes and mills that came with three-phase motors on. Okay, we don't need that. So that puts us into the other category, the I forgot what you call the older VFDs that do not have sensorless vector. Alright, so I'm standing down here in the basement, and it just occurred to me that this boiler's probably been coming on the whole time I've been talking, and hopefully the audio is going to be okay. So what we were talking about before the phone rang, and I got interrupted, was we had said, okay, we don't need the closed loop thing, and those VFDs are going to be big money. And because you're going to buy a motor with an encoder, and yeah, we don't want that. So now we're going to go with the other. So, well, alright, so why were those drives, those FM50s or TM50s, or why were those drives so cheap? So, well, because they're perfectly fine for many applications, but they actually are the older generation. Matter of fact, some websites actually refer to those as a legacy drive. And I've heard legacy drive before, but the funny thing is, the legacy drive usually, you think of like hard drives or something like that for a computer. I think it's a term that's born from the computer industry. And depending on which definition you decide to go with, it can mean anything from obsolete to no longer available. But essentially what we're dealing with here is we're dealing with a drive that is an older design and has been replaced by this newer series, I think it's the EV series of drives. And what the main difference is, from my understanding, the main difference is that the newer series drive has the sensorless vector feature. And what that essentially is that's a drive that has some of the capability, or it can do some of the things that a closed loop system with a motor with an encoder can do without actually having the encoder. What it does is it actually monitors phase, voltage, and current constantly as it's being fed to the motor, and is able to make corrections accordingly. This is all really boring stuff. Here's what you need to know. What a sensorless vector drive can do for you that a drive that does not have sensorless vector. The main thing it can do for you is it can give you much better torque performance, especially at lower speeds. So essentially what's going to happen is the VFD is going to decrease the frequency. It's going to manipulate the voltage and current so that when you decrease the frequency to the three-phase motor, it's going to slow the motor's RPMs down. So you can slow the motor down. So now you get a speed control for your motor, which is great. And anybody who's ever tried this before will tell you, if you take a regular 120 volt single phase or a 220 volt two-phase motor that is rated for, say, 3450 RPM, and if you try and do something cute, like run it through a device called a variac, which allows you to drop the voltage down, okay, to the motor. Yes, it will slow the motor down, but what will happen is your torque will drop off real quickly, and you'll have big problems. If you try and run a regular motor that's rated at 3450 RPMs, and you try and run it way down low in RPMs, it's probably going to stall and not even be able to restart itself, unless you turn the voltage back up and give it a little kick. So what's great about the VFD is, well, now we can turn the frequency down low, we can slow the motor down, but we can still maintain our torque. And we can do it really well if we've got a sensorless vector drive. And we can do it incredibly well if we go with the closed loop with the encoder, but we already talked about that, it's so expensive, and we're not doing that. So I recommend the sensorless vector drive. And now the prevailing wisdom now is, scales of economy kick in, and the prices come down on devices, and now it almost doesn't make sense not to get the sensorless the drive with the sensorless vector. If for nothing more, then you're getting a newer drive. You're getting a drive that's got a newer design, and it's got some design improvements too. So my recommendation would be to look for a Teco or some brand that has sensorless vector. And you're going to probably, when you do a price comparison, you might not find much of a difference. So let's look at one of the drives on Factorymation, okay? And then we'll have to go over to Wolf Automation and do a comparison. For our comparison purposes, we're going to look at the drives, same horsepower. We're going to pick 3 horsepower because that happens to be what I ended up going with. Oh, and I want to say something about that too. I stopped talking about that really cheap drive before. I was saying, hey, safety issues possibly, workmanship issues possibly, yada, yada, yada. Another thing you got to worry about with some of those cheapy drives is you got to worry about the specifications they're giving you. You're going to see a lot of drives where they don't tell you the horsepower that the drive is supposedly supposed to run. Or you'll see a horsepower and it might not make sense. And you kind of want to almost look at the wattage. So I think a 3 horsepower is somewhere like around 2200 watts, or you'll see 2.2 kW. If that's wrong, I'll correct it, put it on screen. I think the 2 horsepower is going to be like 1500 watts or 1.5 kW. Okay. But you want to look at what the full load amps, I think that's the specification, the amperage that can come out of the drive and go to the motor. You want to look at that. You want to look at the nameplate, the data plate on your motor that you want to run. You want to make darn sure you've got a drive that's capable of doing that. And in my case, I could have gotten the 2 horsepower drive because I've got a 2 horsepower motor. But I went one size up to 3 horsepower. And I had planned on doing that even before I found the deal drive that I ended up buying from the guy in Texas. The reason why I went up one more is because I look at it this way. It's kind of like you go to buy a lawn tractor to cut your lawn. And a lot of guys are going to hate this analogy, but it's the one that comes to mind. And you look at the lawn tractors and you're going down the line, and if apples to apples, oranges to oranges, everything's correct. And this one's got a, let's say, a Briggs & Stratton Vanguard or Intech or whatever, 18 horsepower. And then you go down the line a little further and there's one with a 22 horsepower or 25, okay? And you look at it, gee, the tractor's not that much bigger. You can fit it in your shed or whatever, and the cutting deck's a little bigger, and oh, gee, do I need that? Well, a lot of guys are just going to gotta have the horsepower, so they're going to go towards that. But there's another reason why you might actually want that. I think of it this way. I think of it as that motor has that extra power available. And even if you don't use it, it's there. Therefore, maybe, just maybe, that motor breathes a little easier when it's doing, less work. The 3 horsepower drive, it's got a big old heat sink on the back because it has to be able to take that rated amount of current power going through that thing. Well, what that tells me is that if I've got a 3 horsepower and it's capable of that, and I'm only running my 2 horsepower off of it, that thing should run cooler. And in my mind, anytime you can keep your electronics running cooler, you're increasing the longevity. Not only that, any heat given off by any electrical device, other than a device that's supposed to be heating something, is wasted energy. Basically, you're wasting energy. So I think I've pretty much covered what I wanted to cover. If you want to see my drive get wired up, see some of the little head-scratching moments I had because I can't read the manual that well, and where I had to run back to the internet, ask for help, things like that. If you want to see all those trials and tribulations, if you want to see the drive run, if I have time on this video doesn't get too long, I'll throw a little quick demonstration on the end of this video of I've got the drive only temporarily wired up right now. If not, then I'll put a link to my Wells Index video where I start the whole process of wiring the drive and going through it. Okay. So thanks, and thanks for watching. If you like what you see, please hit the like button. If you don't like what you see, please forget you were here. Yeah. Comments are welcome, appreciated. I guess that's it. All right, so here's my Teco EV series drive. And this might look a little bit different than some of the ones you see online because this is the one that's it's a NEMA 4 enclosure. So the actual drive is physically a little bit smaller than this. When they put it in this enclosure, it's all self-contained. Basically, you can bolt and screw it right onto a wall or a machine cabinet or whatever. It's got a huge aluminum heatsink on the back here. And the other big difference is if you get the regular drive, the input wires are going to have some way of turning the power on and off to the input of the drive. Whereas when it's in the NEMA 4 enclosure like this, all the ones I've seen with the NEMA 4 come with this big on-off switch. And this is not a logic state on-off switch. This is actually a switch that's right on the input. These wires, this cable I have temporarily coming in here, it goes right to this switch. So when this is off, absolutely no electricity is allowed to get into this device. And that noise you hear before I started the drive, we're right here near the boiler, and I was hoping it would shut off, but the problem is it's been on standby all day and it's now just starting its heating program. That's going to run for a while because I was hoping this wasn't running so that you could just hear what this sounds like because this is so quiet. So last time I was playing around with it, I left it at this flashing. This is normal for this to flash, and this will say 32.2. And also, if you don't have the, if you have the really basic version of this, you're going to find that to start and stop and change the frequency, you're going to use the up and down arrows and the stop run button. And in my particular application, the stop run button actually does nothing because I have a parameter that's been set because a different way, because instead of changing the frequency through here, see it says ER1. The reason why it's doing that is because I have these controls down here. This is actually a stop, forward, reverse switch, and this is a potentiometer that's going to change that frequency. You can see it's changing. So if I crank it all the way up, that's 60 hertz. That's the max that the factory default is set for. I can actually go in there and change that. So I can overspeed this motor if I wanted to. But anyways, I'll go back to about halfway there. So call that 30 hertz. So there's a ramp up time that can be actually changed, and that controls how long it takes for the motor to go from a stop state to whatever the set RPMs are, or the RPMs that correspond to that frequency. You'll notice that it doesn't just shut off. It literally makes that frequency go down slowly. So the speed that went from 30 down to 0 and stopped, actually there's a parameter in there, you can change that. So I'm going to end up changing a lot of parameters and changing some things. There's also presets. You can have preset speeds in here. A ton of stuff you can do. The beauty of a microprocessor, control, and the kind of things you can do. Pretty impressive. Reverse. Okay, so now you can hear the drive. Most of that noise, if you can hear it, it's just a slight whirring sound. Most of that noise is a cooling fan that's blowing right on the insulated gate bipolar transistor pack that is bolted to the heatsink. It's all about keeping that puppy cool. I mean, I haven't really run it very long, but I've run it pretty slow. Well, guys, I'm having a problem. I can't get my range selector here into the high range position, so I guess I'm not going to be able to run it at full speed till I figure out what's going on with that. But getting back to the VFD, the other thing I needed to cover that I didn't mention was I've got the output of the VFD, which is labeled T1, T2, and T3 for the 3 phases, going directly to the motor. The reason why I want to mention that is because I have, you can see, I've got a drum switch right here. And originally the way the drum switch worked was this was off, this was forward, and that was reverse. Which is all fine and dandy if you've got regular 3-phase power coming in. But VFDs do not like to have any switching between the output of the VFD and the VFD itself. In other words, the VFD wants to handle all that switching for you, stopping, reverse, starting, all of that. So what I did was I bypassed this switch. So this switch does nothing right now. Now later I might change this switch. I might use this switch in a different capacity. I might actually use it with some low voltage wiring to run back to the VFD. And basically, you know, that little knob on the front that I'm turning, that little plastic knob that goes forward, off, reverse, I might basically just have this switch do that job for me. So I can have my mill side control back. A lot of guys actually mount just a separate box with an emergency stop switch, a little potentiometer, speed control and everything right here at the side of the mill. So I might do that too, I don't know. I haven't decided yet. But next thing I gotta do is I gotta figure out why this isn't shifting on me. Alright, but that concludes my my little talk and demonstration about VFDs. I have no way, I don't